Welcome to Genesis. I'm Nina Sansa, and I have the breaking news. Australia threatened to fall into darkness as the mines have stopped producing and transporting coal. We now go to Scarlett at the scene.
Thanks, Nina. I'm now at the mine site where this catastrophe began. I have one of the local coal mining engineers here, Jack. Welcome, Jack.
Thank you.
So, Jack, can you please enlighten us on why the coal mines have stopped providing and shipping coal?
Well, Scarlett, the catalyst for this misfortune event is simply to do with the lack of mathematics used in the worksite.
You don't need maths in the coal mining industry, do you?
Actually, Scarlett, you're wrong about that. You need maths everywhere.
Part of Jack's interesting job as an engineer is determining the ratio of overburden to coal. This will help Jack to determine if the coal is economically viable to excavate. Jack uses drawings to show you this process of calculating the ratio.
To achieve this, we drill down and attain the depth measurements of both the overburden and the coal. We determine the quantity of each amount, and then we calculate the overburden to coal ratio.
For our example, we've constructed this diagram to assist us to model the process. The dimensions of the overburden are 70 metres long by 20 metres wide and 60 metres high. The formula we need to determine volume is length times width times height. The volume of the overburden is calculated by timesing 70 by 60 by 20. This gives us a volume of 84,000 metres cubed. We use the same formula of length times width times height to determine the volume of the coal. The dimensions of the coal are 70 metres long by 10 metres high by 20 metres wide. This gives us a total of 14,000 metres cubed. We use the ratio 14,000 to 84,000 and simplify that by dividing it by 1,000. This gives us a new ratio of 14 to 84. We can simplify this further by dividing both sides by 14. Our new simplified ratio for coal to overburden is 1 to 6. This is the desirable ratio to excavate the coal.
However, the ratio viability differs from mine to mine.
Once the coal has been excavated, it needs to be washed and transported to the customers of the mine. Many of these customers are overseas, so the coal will need to be shipped to these countries by boat. The coal is loaded onto trains at the mine and then transported to the port.
1 metre cubed equals approximately 1.4 tonnes, but that depends on the ash content in the coal. When we convert our 14,000 metres cubed into tonnes, we multiply it by 1.4, a total of 19,600 tonnes of coal. For each train, there are 95 carriages, and it just so happens that each carriage has a capacity of 95 tonnes. To work out the total capacity of each train, we use the equation 95 times 95. So this gives us a total of 9,025 tonnes per train. Our next step is to take the total load of coal that we ship to port. We then divide our amount by how many tonnes per train. This means we require approximately 2 trains to ship all our coal to port.
Thanks, Jack, for that incredibly exciting visit to the mine site.
I hope I showed you the importance of an increase in mathematics skills in the mine site. Otherwise, we'd have catastrophes like this continuously.
Now, crossing back to you, Nina.
Thanks, Scarlett. Luckily, Jack is going to increase the amount of mathematics used in the worksite, making a brighter outcome.